So let's talk about higher order partial derivatives. And this concept is pretty straightforward. If you could take one partial derivative with respect to x, you could also take another one. Likewise with y. You could even take a partial derivative with respect to y of a function whose partial derivative with respect to x you took. Okay? So here we have an example where we're asked to find the four second partial derivatives of this function of two variables. Okay? Now let's see why we have four. In order to take the second partial derivatives, we should start with the first partial derivatives. So we have the partial derivative with respect to x of the function f. And here again, what do? We just treat y as some constant. As we're taking a derivative, the partial derivative, quote, distributes over sums and differences. Okay, that's just born out of its limit definition. So distributing this partial derivative across the sums and then treating y as a constant so that you factor out a y, if you will, pull it out of the derivative. Then we're left with evaluating these partial derivatives. Finally, you are left with that term there at the end. We could do the same thing with respect to y, this time a little faster as we're getting more used to this. So okay, treat x as a constant and just go through all these other terms with respect to y, and you will get this term here. So that's the partial derivative with respect to y. When we want the second derivative with respect to x, so that the second partial derivative with respect to x, we just, this here is notation. What you're seeing, all of this is notation. I just would like you to see alternative ways of denoting this concept. So here this is all just notation, but this part is significant. We want to take the partial derivative with respect to x of what? Of the first partial derivative with respect to x. So what's going in here is fx. Okay, f sub x, fx. That's what goes in here, and then take another derivative with respect to x, and we get this term here. We do the same thing with respect to y. What is the partial derivative, second partial derivative with respect to y? Well, it's the partial derivative with respect to y of the first partial derivative with respect to y. So this is the same as that. Okay? Now when you take that partial derivative with respect to y, you're left with that term here. And this notation here is telling you that we're taking the partial derivative with respect to y of f sub x. Okay, so this y, which comes second, is the derivative that we take second. So here we have the partial derivative with respect to y of the partial derivative with respect to x. That's denoted by this guy here. And well, what is the partial derivative with respect to x? We already computed that up here. So that's what you're seeing in here. Now take its partial derivative with respect to y, and you get this term here. What about taking the partial derivative with respect to x of the function's partial derivative with respect to y? Okay, so again, this x comes second means you take the derivative second. So doing so, here's our partial derivative with respect to x. We take this and plug it in here. Okay, those two are the same. And so we get this term at the end. Notice that these two are equal. Okay, and that happens quite often. We have a theorem by Clera, which tells us that if f is defined on some open set of the plane, okay, and crucially fxy and fyx, so fxy is the partial derivative with respect to y of the partial derivative with respect to x, okay, and fyx, if they're both continuous throughout D, then we have that these two are equal at all points of D. So the condition is that these two need to be continuous on the open set D, and then you're guaranteed that, just as we found here, these two will be equal. And also a note on the notation. Take a look at this guy here. What does this mean? Okay, here's how you read it. From left to right, okay, that's the order of derivatives you're taking. So how would this work? Well, this x here represents the last derivative that we take. Then the second to last. Then look at that y there. That's the second one that we take. And this x here denotes the first derivative. Okay, so you read from left to right of these subscripts, and from left to right you're given the order. The first one on the left is x, there's an x. The second one is y, there's a y, and so on. Now, to generalize to functions of three variables is straightforward. You can take the partial derivative with respect to z by just treating x and y as constant, basically. And let's take a concrete example here. Consider the function of three variables this time. And we want to compute the partial derivative with respect to z, not at an arbitrary point x, y, z, but specifically at this point minus 2, 3 pi in space, okay? In 3D space. So we want to evaluate the partial derivative with respect to z at this particular point that we're given. So what do? We take the partial derivative with respect to z. We just treat x and y as constants. Just pull them right out of that derivative, just as if they were constants. And take a derivative of sine z with respect to z. Well, the derivative of sine with respect of sine z with respect to z is just cosine z. And well, this here is the partial derivative with respect to z at the arbitrary point x, y, z. We want it at minus 2, 3 pi. So what do? We just plug in that point. Okay, so here we have minus 2. Why? Because there was an x there. And y is 3. We're giving the value y equals 3. The point with y equal 3 there. And for z, we plug in pi. And we end up getting negative e to the 6th power.